Today we're going to start a new topic. We're going to look at Bayesian learning. What we've seen so far is this question of what does it mean to learn? And we've seen this question multiple times through the semester, 2 times actually. Once in the context of mistake-driven learning or online learning, where the goal of learning was to minimize or make zero the number of mistakes as the learner encounters more data. And we define success as minimizing the number of mistakes. We also looked at pack learnability, and that exploration led us to this discussion of sample complexity and all this bounds on how many examples you need for good generalization. And in each of these regimes, there are different learning algorithms. In the mistake-driven context, specifically, we looked at perceptron. Under the umbrella of pack, we encountered SVM, we encountered boosting, and all that. And in all cases, the learner produces a classifier or a regressor, and that object takes a new instance and produces a label. It always produces a label. Today, we're going to change the game a little bit. First of all, we'll think about a new answer to the question of what does success mean? What does it mean to learn? And this question, we're going to address it from the Bayesian perspective. There are numerous learning algorithms in this regime. We'll be looking at logistic regression. Unfortunately, we'll have to skip naive Bayes because of time constraints. Specifically, today's lecture is an introduction to Bayesian learning. We'll be looking at two named criteria for Bayesian learning, which are called maximum a posteriori and maximum likelihood estimation. And the hope is that by the end of today's lecture, we'll work out 2 examples that illustrate maximum likelihood estimation, one with a binomial distribution and one with a normal distribution. Realistically, I think we will probably have to move the normal distribution thing to the next lecture, but let's see. So let's start with Bayesian learning. When people say probabilistic learning, there are 2 different things that tend to get conflated under the same banner. One of them is you learn a concept that is a probability, that produces a probability. So typically, what we've seen is the learned concept is, if you think of, for example, classifiers, the learned concept is a label, either it's +1 or -1, for example. But nothing says that the learned concept cannot be a probability distribution itself. What's a probability distribution? It's a function that takes an input, and from the context of from the perspective of this learner, it needs to produce a function that takes the input and returns a number between 0 and 1 that is associated with the probability of some event being put. So, for example, 3 of x could be what's the probability that the label is +1, or what's the probability that it will rain tomorrow. So the concept that's being learned is not the actual predictor of the label, but a probability over the label. And you can use that probability to do whatever you want. You can threshold it at half to decide to come up with a label, for example. If the probability of rain is more than a half, then you're going to assume that the label for rain is 1. And it turns out that the kind of learning theory that we've encountered so far, the sort of mathematical tools we've encountered so far, can actually be applied here with a little bit of extension. There's another thing that also shows up under the umbrella of probabilistic learning, and this is Bayesian learning. Here, the idea is we use a probabilistic criterion to decide which hypothesis to favor. In other words, no matter what learning algorithm we have, it uses some criterion to search the hypothesis space. It uses some definition of the best hypothesis given the data. And Bayesian learning relies on the notion, basically Bayes' theorem, to decide on that hypothesis, to decide on what it means for learning to be successful. The hypothesis itself could be a Boolean function. It could be a linear classifier. It could be anything. So this is a difference that it may seem like I'm splitting hairs, but these are two very different things. Bayesian learning uses a probabilistic criterion. The probabilistic concepts are concepts that actually produce probability. The reason I'm actually doing this, I mentioned illustrating the difference, is because, as we will see when we come to logistic regression falls in both these things. The concept itself is a probabilistic concept, and the learning method is the criterion for what is good is Bayesian. So we use a Bayesian notion to learn a probabilistic concept. We'll get there very soon. Any questions?
So, Bayesian learning, you're saying probability function.
Yes.
Which is kind of like happening.
Well, not quite. In fact, learnability, the criterion that's used is not based on a probability. We have in fact learnability, we're asking what's the probability that this classifier will have an error. Sorry, in fact learnability, the error is defined in a probabilistic fashion. The error is the probability that the model makes a mistake on a future example. And we are analyzing the following sort of construct. With high probability, with probability less than greater than 1 minus delta, we will find a classifier that has no error. But at no point do we say the criterion that's used to find the classifier itself is probabilistic. Right? For instance, for SAM, the criterion that was used to find a good classifier was minimize the loss or maximize the margin. Actually, it was maximize the margin. In Bayesian learning, the goal, our goal is to find, in any kind of learning situation, our goal is to find the best hypothesis inside the hypothesis space, capital H, and search to help us with the search. We have some observations, some data that's in capital D. In Bayesian learning, we define best to be the most probable hypothesis in the hypothesis space. Now, this may seem rather, it may seem like a natural thing, but saying that the best hypothesis is the one that's most probable requires us to somehow characterize the probability distribution over the hypothesis space. Because once we have that, then we can basically enumerate every function in the hypothesis space and ask which one is the most probable. So we need to define mathematically and in a computable form, we need to define a probability distribution over the hypothesis space. To do that, we need to know something. We need to make some assumption about the relationship between the data and the hypothesis that's observed. In other words, given this data, we need to assign a probability distribution over the hypothesis space. So we need to come up with some relationship between the data and the hypothesis space, and we'll look at an example that hopefully will make this clear. More generally, it turns out that you can be I'm saying you can be Bayesian, and I have it in quote. You can be Bayesian about other things like the parameters of the model. What I mean by that is you can assume that the parameters of the model are random variables, and you want to find the distribution over those parameters given the data set. Or you can be Bayesian about hyperparameters. You can be any unknown that you want to estimate, you can be Bayesian about that. And by that, I mean, you can assume that it's a random variable that's conditioned on other things that are known. And then you can use Bayes' rule to kind of help you massage that random variable, the conditional distribution, to something that you can work with. This may see, the title of the slide says the basics, but I also realized that I've kind of talked about a lot here without actually giving any detail. The rest of today's lecture is to kind of get into those details. But before we get into the details, I want to kind of talk about, I would like to talk about what Bayesian learning allows. Being Bayesian, in other words, assuming that the model that you're learning is the classifier, the choice of the classifier is a random variable conditioned on some data set. Now, it leads to natural and practical learning algorithms. In fact, it leads to mechanisms to construct learning algorithms, just like we saw with loss minimization. In fact, we will see eventually that these two perspectives are complementary to each other. It gives a systematic approach to combine prior knowledge that you may have about the hypothesis space with the observations that you have. And this is a very important property that the Bayes rule sort of instantiates. If you knew something about the model, if you knew something about the hypothesis space, if you knew that my hypothesis space has 100 functions, but these 50 are extremely unlikely, these 50 are more likely, independent of any data. I don't know how you know that, but let's say you know that information. How would you incorporate that information into your existing learning algorithm? The Bayesian perspective gives a natural mechanism for doing it. It also gives you a framework for thinking about other learners. We're not going to touch the topic much. And it gives you tools for analyzing learning as well. We'll not go into the analysis part of this here. The heart of all this is the Bayes theorem. Show of hands, how many people have seen the Bayes theorem before? How many people understand the Bayes theorem? Everyone does that every single time. Everyone's like, yeah. Let's try to kind of unpack this. You have random variables x and y. Bayes theorem simply says p of y given x is nothing but p of x given y times p of y divided by p of x. This is just shorthand for the probability that that we have y takes the value little y, given that x takes the value little x. And the way to read that is everything on this side of that bar is observed, and everything on this side is something that we would like a distribution over. So the left-hand side is just a probability distribution over over the possible assignments to the capital Y. So Bayes rule says probability that capital Y takes the value little y, having seen that capital X takes the value little x, is exactly the same as this expression here. I'm never going to write this again. And almost never will I write it like this because it's just too verbose. So for the most part, I'll be using this shorthand. Let's stare at this a little bit more and take a look at what this means. Let's go from the far end there. So we have P of Y. P of Y says it's called the prior probability. Notice that that expression is not conditioned, meaning this is just, there is no given anything. It's just P of Y. This is just asking, what is our belief in that random variable before we observe anything, before we observe X in particular. So it's before any observations are made, what's the probability the random what's our knowledge about the random variable Y? The middle term is called the likelihood. Had you chosen a particular value of Y, what's the probability that this particular X that we are currently observing would be the one that we see? So it's called the likelihood term. What's the likelihood of observing a certain X given that Y took a certain value? And the right-hand side is called the posterior probability. What's the probability of Y given that you've seen X? Now, compare the posterior and the prior. They are both probability distributions about the random variable Y. The prior is a distribution that's unconditioned. Before seeing any input, before seeing any observation, what's your belief about Y? The posterior is conditioned. It's just it's the same random variable, but how has your belief changed after having seen X? There is that term P of X at the bottom, but we're not going to talk about that much, simply because we'll never really worry about that. X is observed, Y is the one that we care about. The important point here is the posterior probability is proportional to the likelihood times the prior. The prior is our prior knowledge about the random variable Y. Posterior is after having observed some data, what's your belief about the random variable? And Bayes' rule says these two things are proportional to each other, and the constant of proportionality, or the ratio in which they are proportional, is the likelihood term, which P of x given y. Now, proving the Bayes rule is actually rather straightforward. I'm not going to try to prove. I'm sure you've seen this before. If not, if you think about it a little, you'll be able to prove. But it turns out this is a rather profound thing, because it does not really care about what x is and what y is. X can be an input and y can be a label. X can be a data set and y can be a classifier. In all cases, they're asking what is our belief about y given x. And that's what I mean by we can be Bayesian about anything. X can be a training data set, and y can be the label about a particular future example. There are many possible choices that you can make here. The other thing that I wanted to quickly go over, actually I'll just flash the slide and go past it, is a quick refresher on probabilities. You've seen this before in high school or something. There's the product rule. The probability that you have two random variables A and B together is nothing but probability of A given B times probability of B, which is the same as probability of B given A times P of A. There's some rule that says the probability that A or B is true is probability of A plus probability of B minus probability of A and B. The definition of independence is if you have two random variables A and B, their joint probability, the probability that those two events A and B occur together, is nothing but the product of their individual probabilities. Or equivalently, probability of A given B is exactly the same as probability of A. Having observed B, our belief about A does not change. The probability of A given B is the same as probability of A, which means A and B are independent. You can do the same thing about probability of B given A. And then there's the theorem of total probability. If you have mutually exclusive, I'm going to skip this for now. You can, I'm sure you've seen this before. If not, you know where to look it up. Let's come back to learning. Our goal with Bayesian learning is we are given a data set. And actually, with all of learning, right? We are given a data set, and our goal is to find a classifier, a hypothesis. And our goal is not just to find a hypothesis, but the best hypothesis according to some criteria. And we can define the word best in different ways. We can operationalize it in different ways. Bayesian learning uses the probability of the hypothesis given the data to define the word best. We want to find the most probable hypothesis given the data set. Having observed the data set among all the hypotheses that are possible in the hypothesis space, our goal is to find the best, the most probable one, which means the probability distribution of interest here is P of H given D. Before I start applying the Bayes rule to this, are there any questions about this? Yes.
So basically, you're saying I was like probability of getting the right continuous.
Yes. As we observe data, well, let's not worry about the change. We don't care about the change as much as what is the probability of the hypothesis H being the right function, given that we have among all the data sets that might exist, given this is the one that we have showed up at our doorstep. Given that this is the data we have, what's the probability that H is the true hypothesis? You have questions?
So we still assume the distribution is the same distribution.
We are not necessarily making such assumptions. We are implicitly, we will be doing that, but not implicitly. It turns out that it exists. The idea that the distribution of the data is not going to change shows up, but actually it is not the distribution of data, but the conditional distribution of the data given the hypothesis. We'll come to that in a minute. Did you have a question? Okay. So let's apply the Bayes rule here. Our goal is to find the probability of the hypothesis given the data set. This looks like a posterior probability. what is the probability that H among all the hypotheses that exist, H is the hypothesis, given that the data set D is observed. Now, the cool thing that that takes a little bit of thinking to appreciate is that both H and D are actually events. Little h is the event that among all the hypotheses that exist in the hypothesis space, this particular one is the true hypothesis, the one that nature chose, or the one that nature uses. Capital D is the event that among all the data sets of this size that could exist, this is the one that we observe. Both of these are events, and that's why we can write this probability distribution. And nothing says, the Bayes rule does not really care about what random variables you're working with. You can apply the Bayes rule here. So just blindly, you can say that probability of H given D equals probability of D given H times P of H divided by P of D. I've done nothing fancy here. I've just applied the Bayes rule. But now we can start thinking about what these expressions mean, given that we know these random variables have a certain interpretation. The posterior probability, let's start with that, P of H. This is the probability that that H, little h, is the true hypothesis before we encountered any data. This is our expectation about the hypothesis space. In the absence of any data, you prefer this hypothesis over that. That's one way of thinking about it. Another way of thinking about it is, if there are two hypotheses, H1 and H2, that equally explain the data, would you prefer H1 or H2? What would your preference be? How would you choose the hypothesis? This is in using information that is not expressed in the data set. Can you impose preferences on the hypothesis? We've done this before. We've played this game before. For SVM, for example, the regularizer does this job. The regularizer says, independent of any data, there's a preference on certain types of hypotheses over certain other types of hypotheses. The specific preference that we seek to impose with the squared norm L2 regularizer is we want to make the weight vector 0, for example, in the absence of any data. We are penalizing complexity. This idea that we are penalizing complexity is independent of any data set, and that sort of preferences can be encoded. Those sorts of preferences could be encoded into this prior. And then there's the likelihood. The likelihood term says what's the probability that this data set would be observed had the true hypothesis been H. This data set could contain one example or many examples. Either way, we can ask the question: what's the probability that this data set is the one that exists had little h been the true hypothesis? There's the term at the bottom, P of D. That's just asking what's the probability that that data set D is observed, independent of any knowledge about any hypothesis. And we've seen a bit that this term is not going to matter for us. So we are not going to spend too much time worrying about that. Any questions about any of this stuff? Yes. Data consists of both examples and labels. So it's how we extract, how we generate the instances, and how they get labeled. So it could be both. Yes.
The data exists. What do you mean by the probability that we have? Like, how likely we are to see it show up in nature?
Yeah. How likely are we to see this data set show up in nature had the hypothesis been realized? I'm talking about the likelihood term. But I don't feel like I have convincingly answered your question, so ask me a question. Or did you have a follow-up?
some
Mhm.
lives. And outlier super likelihood of observing that data point if the true function is actually that.
So in fact, let's look at it. Let's actually draw that example. So let's say that I have a data set that looks like this. These 5 examples. And let's say we are working with linear regression. And so we have 2 dimensions. We have an input and a label. And now I could ask, and let's consider 3 different hypotheses. H1 is this line here. H2 is this line here. And H3 is this curve here. And I could ask, had H2 been the true hypothesis, what is the probability that nature would have generated this data? Maybe nature could have picked the same x's, but had H2 been the true hypothesis, you would have seen these y's. So those red points are extremely unlikely to have shown up in to be in the data set, right? It would have you'd have needed a lot of noise for these black circles to become the red points. So that was the example. That's the intuition. Whereas H2 seems like it may have been the hypothesis. There's an outlier here that it doesn't explain, but it's better than, sorry, I see I have 2 H2s here. That's so. I don't know why I started counting at 2. Okay, so H1 seems like it would have been more likely to show up in nature. There's an outlier, but maybe that's, all data has noise. H3 seems also reasonably good, but then H3 is more complex than H2, and that's where the prior might come in and say, yeah, I prefer H1, sorry. I prefer H1 over H3. So the likelihood term will impose a preference between H1 and H2. The prior might impose a preference between H1 and H3. Other questions? I thought there was another hand somewhere at the back. Did you? Yeah.
So basically, I was just talking about fire. Basically, you got almost within fire was whatever we wanted to set that to and higher than so like you said,
The prior allows you to impose preferences that are independent of the data, independent of any observation. And this is a conceptual framework at this point, and when we look at examples, we'll have to start thinking about which priors we actually use, and that becomes an interesting sort of a exploration of its own, because the prior itself could be conditioned on other things. You can have layers and layers of you can be Bayesian about the prior, and then it gets more complicated. But we're not going to even see that right now. Given this setup, let's now look at 2 different criteria for learning. There are questions. How do you know P of H and P of D given H? It seems like it's very hard to know. Let's go back. It seems like it's very hard to know the probability of a hypothesis or probability of seeing a data given the hypothesis. That's a good question. It turns out that we're not done. In order to actually operationalize this and come up with actual criteria that we can use for learning, we need to instantiate P of D given H and P of H in certain functional forms. And this will require us to make certain assumptions. And every application will need its own assumptions, or rather, every type of model might need its own assumptions. So we'll see 3 instances of how this can be done. There's a question that is not related to this about the final exam. Will the final exam include the content before the midterm? No, it will include everything that was not covered in the midterm. Okay, so let's now look at these 2 criteria for learning: the maximum a posteriori and the maximum likelihood criteria. The maximum a posteriori hypothesis, which maximum a posteriori is a very complicated phrase to say, so I'm just going to say max. So the map hypothesis is simply the most probable one. The most probable hypothesis given the data set. So what we do is among every oh no. Among every hypothesis that might exist, we find the one that has the highest value of P of H given D. And the thing is, we know how Bayes rule works. So P of H given D is nothing but P of D given H times P of H divided by P of D. And this is the place where I'll explain why we don't really care about P of D. Notice that P of D here is in the denominator, which is in the denominator, is independent of the thing that we are searching over in our maximization. In other words, P of D is, as far as the thing that we are varying, H is concerned, P of D is a constant. We don't need to compute that thing because it's all we care about is the relative ordering between the hypotheses, and the numerator is sufficient. Just to remind you, in this thing here, this thing is the P of D given H is called the likelihood, and P of H is called the prior. So map learning simply requires us to find the hypothesis H that maximizes the product of the likelihood and the prior. The likelihood is the likelihood of the data given the hypothesis. The prior is the prior probability of the hypothesis. Questions? Questions about map learning? Yeah.
Would it also be fair regarding the word probability? Would it be fair to say that the probability of uncertainty is one because it's uncertain?
No, not necessarily. It's not one because we've observed it. Because really, just to kind of make it make this technically correct, this denominator there, P of D, is nothing but, I'm going to write this here, P of D is the sum over all the hypotheses it's this expression there. Because it serves as the normalized, the thing inside the summation is exactly that. So we are enumerating all possible hypotheses and asking, is this the hypothesis that generated, either this hypothesis generated the data or that hypothesis, each one, and you are adding up all of these things over all the hypotheses and asking for the total probability. It's not one because you've observed the data. It's possible that you may have your observation is an extremely unlikely data set, right? And it just doesn't matter because whether it's likely or unlikely, it doesn't affect your choice of the hypothesis, right? Other questions? So how do we choose a hypothesis? The map criterion simply says, find a hypothesis that maximizes the product of the likelihood and the prior. But now this, now we come to the question that came up on Zoom. How do we know what P of H is among there's a question. I'll come to that in a bit. How do we know what P of H is? The prior term. Like let's take a concrete example. Let's say that your hypothesis space consists of all possible decision trees. So you want to be Bayesian about the decision tree learning problem. So now you need to somehow impose a preference over all possible hypotheses, over all possible decision trees. Let's even make it more fairly. Let's say you consider only decision trees of depth 3. So all the trees have the same depth. Now, how do you know which hypothesis is more likely than other, independent of any data? Why might you even have a preference? Right? This is a tricky point. The framework allows you to inject these preferences, but manufacturing these preferences is not always easy. And that's why the most common preference that we have is none. All hypotheses are equally likely before seeing any data. In other words, P of H is the uniform distribution. When that happens, this expression becomes a constant. All hypotheses are equally likely, have an equal prior, and we use only the likelihood term, P of P given H, to find the best hypothesis. So this simplification is called the maximum likelihood criterion, and usually it's abbreviated as ML. ML is a terrible abbreviation in a machine learning class, but that's what we have. So the maximum likelihood hypothesis is nothing but the hypothesis that maximizes the probability of the data given the hypothesis. In other words, it maximizes the likelihood. I'll come to the question on Zoom. Though we can find the most likely hedge, can we never actually know the true posterior? We don't know the true. I wouldn't say never. There are certain problems where we can compute the true posterior, but for the most part, we will not actually ever compute the true posterior because we're going to get rid of this P of D. The true posterior distribution depends, it needs to be P of D given H times P of H divided by P of D. We are never going to compute the P of D because it's just a needless expense. So we'll never calculate the value of that. I'm assuming that's what you meant by your question. If I didn't, just post a comment. Any questions about maximum likelihood hypothesis, the maximum likelihood criterion? These two names are refreshingly correct. The maximum likelihood hypothesis fix the maximum likelihood hypothesis. The maximum a posteriori, you need to know a little bit of Latin, but it just says the hypothesis that is the maximum posterior distribution. So it's easy to remember these things rather than support vector machines. Who knows what that means? Some names are more plain. Yes.
We don't assume the prior is uniform. Like we assume the prior is normal distribution. How is it that this to the maximum likelihood?
No, if you assume that the prior is anything but uniform, you're no longer in maximum likelihood. By definition, it is the maximum posteriority. Maximum likelihood assumes that the prior is uniform. Or you can think of the prior as being uniform or the prior being irrelevant. Because if it's uniform, if all hypotheses are equally likely, then equally probable in the prior distribution, then it does not give you any, it does not differentiate in the hypothesis space. Other questions?
Basically, math equals to HML.
H map is not equal to HML. It's equal to HML only when the prior P of H is uniform. H map and HML are the same thing when the prior distribution is uniform. As a matter of practical convenience, we never work with the likelihood expressions directly. We never work with this product explicitly. Instead, we always operate in the log space. So we don't maximize the likelihood, we maximize the log likelihood. Because log is an increasing function, it's going to give us the same answer. We'll see in the examples that we've encountered, operating in the log space allows for the computation and the analysis to be easier. So the term log likelihood is a phrase, that phrase log likelihood is something that shows up a lot. And sometimes it's summarized as LF of D. That's nothing but log P of data given H. The log likelihood of the data is the log of the likelihood. Now, I've done the same thing that I did with say SVM and other at least a couple of times so far in the semester, where I said the goal of learning is to maximize this this criterion or that criterion, or minimize this or that criterion. I don't talk about how this maximization or minimization is actually achieved. In this case, let me to kind of drive home the point that of what we are actually doing. Here's a brute force map learning. This is a terrible art, never implemented, but it's just conceptually, this is what any map learner should be doing. What you do is this, I see there's a mistake here, this should be H in H. For every hypothesis H in the hypothesis space, we calculate the posterior probability P of X given D. And then we have a big list, possibly an infinitely large list of that maps the hypothesis to its posterior probability. And we find the hypothesis that maximizes, you enumerate this whole thing and find the one that has the highest posterior. And if you do that, you would have implemented a map learner that is mathematically correct, practically a terrible thing, because imagine enumerating every possible linear classifier and finding the most probable one. It's not going to work, but this is, no matter what the optimizer does, it should be equivalent to this. Of course, this makes no sense except for the simplest sort of hypothesis spaces, the kinds that you might encounter, say, in an exam question. In anything practical, you shouldn't be doing this. So far, all I have done is given you the high-level sort of framework for thinking about Bayesian learning. And now we're going to illustrate how this actually works for a few examples. But before that, are there any questions about this idea of the posterior probability of hypotheses given data, likelihood and prior, or about map learning or maximum of posteriority? Or maximum likelihood learning? How many people have seen these criteria before? A smaller number than I thought. Isn't this covered in the foundations of data science? It is? Okay. But one of the things about Bayesian learning is you need to see it a few times and kind of work with it to get comfortable with it. It takes a little bit of getting used to sometimes. Let's look at a couple of examples. The first one is a very simple example. In fact, it's so simple that you can actually get the answer without doing any of the heavy lifting. But then I'm going to make it unnecessarily complicated just to show you that it works. This involves Bernoulli trials. And we're going to focus on maximum likelihood estimation, which means that I'm not going to say anything about the prior for now. So for maximum likelihood estimation, we need to somehow, first of all, we need to assume a hypothesis, the set of functions that we are interested in. And the second thing we need to do is come up with a mathematical way to define that expression. How is the data generated had the hypothesis been some h? And this is where we need to start, we need to apply what we know about a particular problem at a hypothesis space, and we may have to define this for every task. So let's consider a very simple example. Let's say you work for a light bulb manufacturing company, and you need to figure out how the company comes to you and asks, I need to figure out what the probability that the light bulb will manufacture is quantity. And of course, the first question that you need to ask is, are they all identical? The reason this is an important question is because you can make some assumptions about them being identical and independent. Basically, the IID assumption is available. And then, of course, you can't generate this probability just out of thin air. You need to conduct an experiment. Let's say the experiment involves you testing 100 light bulbs. So you test 100 light bulbs, 80 of them work and 20 of them don't. And quite obviously, if that happens, then the probability of failure is 0.2, 20 divided by 100. So far, I hope there are no surprises, right? The question is, why is the probability of failure 0.2? Why is that the right answer? How do you know that's the right answer? Yes.
So, just with the terms of the trial, number of successes, number of failures, and with the probably failure rates, number of failures.
Okay, you have the right answer. Yes. Basically, that's the right answer. Can someone else tell me what that means? That's right. Okay, but why is it 0.2? Why not 0.21? Or why not 0.205? Oh, how do you know that you need to divide 20 by 100? Why is that the right thing to do? Why not 21 divided by, or why not 20 divided by 80?
Because we know all the data.
We don't know all the data. We only have done 100 experiments.
The probability of this hypothesis is most likely given that data for the observed.
That's basically the answer that came up before, and that's really where I'm going. Yes.
I mean, we're assuming that the 100 variables we selected represent the population. But it's
And that was exactly the same answer as what came up before. And that is a necessary condition for deriving what we're going to do next. So let's prove that the answer is 20 divided by 100. So our goal is to find the probability of failure. So we'll get the probability of success as well. So let's say the probability of failure is P. Right? So that means the probability of success is 1 minus P. Each trial is IID. That means every light bulb either fails or succeeds independently of the failure and success of any other light. So if we have seen, let's say we have these 5 light bulbs here, the probability that this one succeeds is 1 minus P. The probability that this one succeeds is 1 minus P. This one is 1 minus P. This one, the fourth one has failed. The probability that it fails is P. The probability that this one succeeds is 1 minus P. So the data that we've encountered has these 5 observations, and the probability that we've encountered this particular data set of 5 examples is 1 minus P power 4 times P, but not quite that, because you can reorder this in any different way. So maybe the failure happened in the first position or the 5th position. Those are all the same. So the failure could happen anywhere. So let's say 5 choose 1 times. That's choosing where that failure shows up. So this is the probability of 4 successes and 1 failure. Right? Let's generalize this. Let's say we have, or let's look at the example that we had. We have a data set with 80 successes and 20 failures. Those 80 successes could be anywhere inside the 100 trials. So the probability of the data, D, given the hypothesis P, is 100 choose 80 times P power 20. P is the probability of failure, and 1 minus P power 80. 1 minus P is the probability of success. So this is the likelihood term, and this hopefully kind of gives you an intuition for how the likelihood is going to get calculated. We made an assumption about the data, about how a single data point, in this case, each data point is a light bulb. We made an assumption about how the data point is generated, and based on that assumption, we are able to calculate the value of the likelihood. This is not the only assumption that we could have made. Maybe the light bulb, the success and the failure of the light bulb depends on where you got the glass from, or maybe it depends on what day of the week it is. Maybe it depends on other factors that maybe who's operating the machine and whatever. There are other factors. Those could be features that go into this decision. If you had done that, then this is no longer a Bernoulli trial. There are other distributions that you'll have to use. In this case, we are assuming that there are no other factors. There's just bad things happen with probability. That's pretty much that's the model we are working with here. And now the question is, what's the most likely value for this observation? The way to think about that is, notice that the right-hand side there is a function in P. And our goal is to find the hypothesis, in this case, is the number P, that maximizes that value. It's a function in P that we are trying to maximize. We know how to maximize functions. We can use calculus. And we can just literally apply calculus to this and solve the problem. So the most likely hypothesis is, or the maximum likelihood hypothesis, is simply the probability P that maximizes P of D given little p, which is nothing but the probability p that maximizes this expression here. I can solve this for this expression, but let's make it a little bit more general. Rather than 100 trials with 80 and 20 working or not working, let's say we have we've done A plus B trials, where A light bulbs don't work and B of them work. And the best hypothesis, in this case, this is the maximum likelihood hypothesis. The best hypothesis according to the maximum likelihood criterion is the one that maximizes P of D given H. But P of D given H, that expression is a little bit painful to work with, so we'll work with the log of that. So it's the same as the one that maximizes the log likelihood, log of P of D given H. And at this point, rather than me showing you the math, let me work out the math. So we know that P of D given H is A plus B, choose A, times P power A times 1 minus B power 1 minus power B. That means the log of this quantity is log A plus B, not divided by, choose A plus A log P plus B log 1 minus B. I can now take the derivative of this whole expression with respect to P. This is A and B are your observation. Given values of A and B, the first term is just a number. The only unknown here is P, and our goal is to maximize that quantity. So I have but the term which means that we can essentially ignore this because that doesn't really depend on P. The log likelihood is maximized by the probability that maximizes just the second and the third term, the sum of the second and the third term. So that's what I have here. I want to maximize A log P plus B log 1 minus B. Any questions? How would you proceed? Take the derivative. There's a question on Zoom that I'll get to later. You can take the derivative of this with respect to P. So I can take, what's the derivative? Help me out here, because this is A divided by P plus B divided by 1 minus P, the minus of that. So just put a minus here. Oh, did I write P? Oh, yeah. Yes, thank you. So we take the derivative. I can set this to 0 to find the maximum or the minimum. It turns out it is the maximum. And so I get A divided by P. I'm going to solve it here. Equals B divided by 1 minus P. A times so the probability, the maximum most likely hypothesis is A divided by A plus B. In the example that we had before, A was 20 and A plus B was 100, and that's why we got 0.2. So this is, in some sense, the explanation for a very long-winded explanation for why it is okay to divide for the answer to be 20 divided by 100. Now, it may not be the only answer. There are actually other assumptions that could give you other answers. I'll talk about that in a minute, but ask me questions. Yes.
Now we need to understand how to get gas and max.
What do you mean? In this specific case or in general?
In general, you will say that concept, but before we see the
Before here, everything about that, everything about this. How do you go from here to here?
No, how do we say we want the best and the best and the next?
That's the definition. That's the definition of maximum likelihood estimation. The definition of maximum likelihood estimation is the hypothesis that this criterion defines to be the best is the one that maximizes the likelihood. Right? And after that, we have to define what the likelihood term is, and then after that, it's this calculus. Other questions? Now, this is, there are many assumptions that have gone into this. I've assumed here that the model that generates the data is the Bernoulli distribution. You could have assumed a different model. You could have assumed other factors that play into this thing. In fact, you could have also assumed a prior. You could have assumed a prior distribution that says certain values of the probability P are more likely than certain others. And if you had assumed a certain prior, then you will no longer get A divided by A plus B. You will end up getting other. Then you'll no longer be maximum likelihood estimation. You'll be doing maximum posteriori estimation, and you'll get something that's different from A divided by A plus B. If you want to kind of explore this on your own, the most common prior that's used in this sort of a scenario is called the beta distribution. And it ends up adding a little bit of something to the numerator and the denominator. So you might get something like 0.21 or maybe 0.205, depending on your choice of hyperparameters. But what we've seen here is the simplest version of things. There's a question on Zoom, is is this an application of Bayesian learning? How can we conceptually relate them together? The way Bayesian learning simply specifies the criteria to decide what is the best hypothesis. But in order to instantiate it, you need to make some assumptions about how data is generated given a certain hypothesis. Here, we have made an assumption that the data, in this case, the number of light bulbs that work and don't work, is generated by independent Bernoulli trials. So every time we have we need to apply Bayesian learning, we need to make that assumption. Possible that that assumption is wrong. Possible that assumption has no bearing on reality, but that's the game that we are playing. And it turns out that that idea shows up also in other criteria for learning, but it's not as explicitly present. It's often implicitly present in how we define, say, our loss function and how we define how the model itself is defined. All of those things, here you have to explicitly make that assumption. We have 7 minutes left. So I'll start off a second example, and most likely I'll not get to the end of it, but we'll pick up on this in the next lecture. So this time I'm going to use the normal distance. And this time it's going to be something that feels more like a learning algorithm. We're going to apply maximum likelihood estimation. We need to define what a hypothesis space is. Given a task, we need to define what the hypothesis space is. And we need to define a model that says how is a data set generated given a hypothesis. Specifically, in this case, let's say that we have d-dimensional inputs. These are inputs that are x, these are vectors with d features. And the output is a real number. By that I mean, we have a regression problem that maps d dimensions to a single real number. So the hypothesis space consists of all possible functions that can take you from inputs that are d-dimensional to real numbers. Next, I need to define how I'm assuming that the data is generated. Suppose my training data was generated suppose we have the following generative story. An input x is drawn randomly from the d-dimensional space. Let's say uniformly at random, which means any point in the d-dimensional space is equally likely. That's technically a little bit mathematically unsound statement, but I'm not going to go there. Now, given that we have a point that is generated uniformly, there is a true function f that we don't have access to that is applied to this data point. So f of xi gives you the label. Unfortunately, your data collection process has some noise. This label f of xi gets perturbed a little bit by some noise called EI. And that's what you get to observe. What you see is not f of xi, but f of xi plus the noise EI. And that is the label that we are that our training data contains. And this noise, we are going to assume, is drawn uniformly, sorry, not uniformly, is drawn according to some unknown Gaussian distribution with zero mean. Because it has zero mean, that means that on an average, it will give you the value of f. It's centered around the value of f, but it can be the deviations are equally likely on both sides. So y is f of xi plus ei. And this process is applied repeatedly and independently many times, m times, and this is how we have generated our training data. Everything here that I've said so far is just a story. And this is my assumption about how the data might have been generated. Maybe this is not how nature generated the data. Maybe there was no noise, the noise was actually part of the true concept. But I have to make some modeling assumption, and this is the assumption I'm making. Any questions about this modeling assumption? I mean, you might argue that this seems unreasonable, but any questions that are not about that? So with this story, let's now try to set up a learning problem. So suppose we have some hypothesis, little less. We could ask, what's the probability that a label y was generated by this hypothesis applied to an example? Suppose H was the true hypothesis. Then the label y is not going to be the same as H of x, because had H been the true hypothesis, there was still some noise that was applied to it that we need to account for. And in particular, the error, the noise, presumably that's the error. The error on this hypothesis is yi minus h of xi. If h was the true hypothesis, then this quantity y minus h of x comes from a normal distribution, because the noise was generated from the normal distribution. So let's say that this particular this noise was generated from a Gaussian distribution with zero mean and some standard deviation sigma. So we can assume, we can compute the probability of seeing this one data point, which is simply this expression here. There is, again, I'm playing a little bit loose with probability density here, and I don't want to get into that discussion. So we can compute the probability of observing one data point, xi comma yi, had the true function be x. And that probability is simply the probability that the error that we encounter is, this is nothing but the probability density for the Gaussian distribution. Any questions? Yes.
And we're geofixing what normally would be yi minus the mean with h of x, right?
Well, no, not quite. This quantity here, yi minus h of xi, is nothing but the error. So we are asking what the problem. The error comes from a zero mean Gaussian distribution. That is the quantity that is normally distributed. Yes.
Probably not clear enough. Previously, I'm not clear about the expression of P, Y, condition, interaction. Now it's been clear.
Okay. Okay. Other questions? This is the probability of seeing one data point had it been generated from the true function, had it been generated from by the function h. Our data set consists of not one data point, but m data points that are generated by the same process independently. So we can ask, what's the probability that your entire data set D was generated according to this function h? This is your likelihood, probability of D, given that h was the true hypothesis. That's simply because these m examples are independently sampled, it's simply the product of P of y comma x given x. Y comma x corresponds to one data set. And it turns out that's that's proportional to P of y given x, and then there's a P of x, which is we assumed was independent, uniform. So that term doesn't show up. So the likelihood of the data is proportional to the product of these expressions, which were all Gaussian. Given the hypothesis. And that's exactly the same as the hypothesis X that maximizes the product of P of y given X comma X. And we are at time, so I'm not going to continue this. On Tuesday, we'll solve this thing, and then we'll see how this takes us back to something that we've already encountered before, and that's kind of cool. And we'll pick up with logistic regression after that. There's a question on Zoom that I'll answer. Why do we need to figure out a label that was generated? And that's because we need to write the likelihood down. That's the reason we are doing this. Okay, I'll see you on Tuesday.